Alright, this lesson is on solving rational equations algebraically. When we're solving equations algebraically, what we're trying to do is we're trying to find a value for x that will make the left-hand side equal to 0. What I'd like you to do is just pause the video very quickly and try and find that value. Okay, did you find that value to be 2? Maybe you just looked at the denominator and said, what does x have to be so that the denominator is 1? Because then 4 divided by 1 is still 4. And so maybe what you did is you wrote this out algebraically and tried to substitute in a value, in this case 2, for the denominator. And when you did that, you ended up with 4 over 1, which of course is equal to 4. So sometimes the questions are fairly straightforward. You can solve them by observation. The next question, there's a little bit more involved. You are still trying to find out where this rational function is equal to this rational function, but to do this by observation can get very difficult. So one strategy, and we're going to be using this a number of times, and there are more than one strategy, but one strategy is to bring both equations to one side so that you can in turn, as we did up here, start to isolate and solve. So what I'm going to do is I'm going to rewrite this out. And what I'm going to do is I notice that this is factorable. So I'm going to factor this right now, see if I can save a step. So x subtract 4 and x plus 1. I am going to bring the entire 3x plus 2 over. I'm also going to bring the x squared minus 1, but I am going to factor it to become x plus 1 and x minus 1. That whole rational minus rational is equal to 0. And eventually, what I want to do is solve for x. So I know that when I add and subtract fractions, I need to have the same common denominator. So if I look at the first rational, I have x minus 4 and x plus 1. Those automatically have to be included in my denominator, the first two. When I look at my second one, I see a common x plus 1, so I don't need to include that anymore, but I do need to include a new x minus 1. And from this point, what I'm going to do is I'm going to show what I need to multiply x minus 5 by so that it has a denominator of x minus 4, x plus 1, and x minus 1. And I see that I'm missing the x minus 1 component. So I need to multiply that through. And the same thing happens with 3x plus 2. I'm missing the x minus 4 from over here. It's on the bottom. So now I do have that common denominator. So it takes a little bit of practice finding these. Now what I can do is I can simplify. So I'm going to multiply or FOIL these out. X squared minus 1x minus 5 more. I'm going to skip a step in here and write minus 6x plus 5. Make sure you can solve for that. Then I'm going to subtract 3x squared. 3x times negative 4 is negative 12 plus 2. So that would be negative 10x. And then subtract 8. And that's all over this common denominator. And so you can see why it's called algebraic, because we're doing a lot of algebra. X squared minus 3x squared is negative 2x squared. Negative 6x minus a negative 10, that's like plus 10. So that's going to give me a total of plus 4x. And finally 5 subtract a negative 8, well that's really plus 8. So 5 plus 8 is 13. And now we're finally ready to start to solve. When we multiply both sides by the denominator, they end up canceling out on this side and equaling 0. So the denominator just disappears, because really what we're doing is we're multiplying it by the same thing. So these two will cancel out, and we know that 0 times these three denominators are going to be equal to still 0. So we end up with this quadratic equation, and we take a quick look at it, and we determine quite quickly that we can't use simple factoring or even decomposition. So we do need to go and solve using quadratic formula. We haven't done a lot of work with quadratic formula, so it's important to refresh ourselves with what the formula is and where to plug in the information. So I I could just plug in the b squared minus 4ac. Remember we called that the discriminant, and the discriminant is just a value that if it's greater than or equal to 0, you have solutions, 1 or 2. If it's less than 0 and it's negative, you cannot take the square root of a negative number, and therefore there aren't any solutions. Now, I've done this question, and the discriminant does work out to a value, so there is going to be a solution here. So let's go and find it. And we'll probably just stop there. But the b value is 4. So I squared 4. The a value is negative 2. And the c value is 13. 2 multiplied by negative 2. Now the important part here is that we end up with a negative times negative, which is going to be a positive. And so we have 8 times 13. 8 times 13, so 8 times 3 is 24, and 2 up there is 104. So this is, as we mentioned before, going to be a solution that has 2 possible solutions. Now, one of the other things that we should get in the habit of doing is try and rationalize this function. And so to rationalize this, what we need to understand or ask ourselves is, with this square root of 120, can it be broken down into one perfect square? And what we know is that 4 multiplied by 30 is still equal to 120. And I chose 4 because I know I can take the square root of 4 and rewrite it as plus or minus 2 root 30. And 30 does not have a perfect square within it, so I'm left with 2 root 30 here, all over negative 4. Now I have one final step, which is to recognize that each of these terms can be divisible by 2. So our final answer looks something like this. And so our solutions are these exact values. Now I use the word exact values. If you see a question that says leave your answer in exact values, then please leave it in the radical form. Do not calculate this to a decimal place. So solving rational equations is very similar to solving rational inequalities. Remember, recall the difference between inequalities and equations. Inequalities have many answers, where equations have only just a few. We can approach the question the same way. The question is looking at, where is this reciprocal of a linear less than 10? And if we're solving it algebraically, remember we could do all these questions graphically as well, especially using the graphing calculator, but we want to solve these using just algebra. And so once again, if you can find a number that you can plug in here that 2 divides into that is less than 10, find the largest number, then that's a great strategy. It's a little hard to see. So one of the ways we could do it is continue and use the same approach as we did with our equations. So I'm going to bring the 10 across and replace the 10 with a 0. I'm going to find a common denominator of x minus 5. And I'm going to multiply negative 10 by the missing x minus 5. I'm going to simplify up top, so I have 2 subtract 10x plus 50 all over x minus 5. And then finally I have negative 10x plus 52 all over x minus 5. Now at this point we're going to almost back to that pseudo technique. And what I want you to do is, just for a moment, I want you to think that that inequality is an equal sign. And if you were solving this using an equal sign, this is what you do. You would multiply both sides by x minus 5. And you would see that this would cancel out, and 0 times anything is still 0. And what you'd be left with is only the numerator. negative 10x plus 52 is equal to, remember I'm going to think of it as an equal sign, 0. I'm going to move the 52 across, and I end up with x is equal to positive 5.2. Now this is where I go back and say, well, you know what, it really was a less than sign, so I've got to change that back. So this is where that sort of pseudo technique comes in. And so this is in fact x has to be less than 5.2 in order for this equation to be correct. And the nice thing about inequalities is you can take 5.2, plug it back into the original equation, and actually test it and see if it is less than 10. If it's equal to 10, we're in trouble. If it's less than 10, then we're okay. So this whole concept of moving everything to one side and solving for 0 is a good strategy. The last question we're going to take a look at turns out to be, looks like a very difficult question, but in fact it's not. So what we're going to do is we're going to solve this quadratic over a quadratic using a similar type method. Okay, the last example we're going to take a look at, example 4, we're going to approach it in similar ways, but we're going to introduce something called the interval method of solving. And it's called the interval method, as you'll see in a few minutes. So the first step we want to do is again understand what it's asking for. What are the values of x that make this statement true, so that the left-hand side is greater than or equal to 0. So they were nice. It was already set equal to 0. So what we can do is I can look at the two quadratics and see if they are factorable. And we see that both of them are. I have x plus 4 and x minus 3. Now, if we treat this one as a equation, we're going to run into trouble. So now our approach is going to be, we're going to introduce a method called the interval method. And the way it works, and we've shown this before, is that we need to identify the critical elements. And the critical elements that we're always going to need to pull out are the x-intercepts and the vertical asymptotes. That's the only information we really need. So the x-intercepts I can see are x equals 2 and negative 1, and the y-intercepts, the vertical asymptote, I can see is x is equal to negative 4 and positive 3. What we then do next is we plot those on a number line. So I'm going to plot them in the same color I wrote them here so we can tell the difference. So I've got 2 and negative 1. Then I have negative 4 and 3. It's not critical that these are equally spaced, but I think by doing them color coding we'll understand what they look like. And what I want to do is I want to plot some dotted lines to show the different intervals that I'm dealing with. So I'm just going to rearrange these and line them up a little bit better. And this is the example where we worked on a previous lesson where we looked at what's called test points. And so what I would like to do is I would like to pick a point to the left of negative 4. So logically I'm going to pick negative 5. And what I'm going to do is I'm going to plug each of the negative 5s into the equation. If this side is greater than, meaning if it's a positive number, or it's equal to 0, then it's part of my solution. So here's what it looks like. I plug in negative 5 here. Negative 5 subtract 2 is negative 7. I'm not concerned about the 7, but I do like the negative. Negative 5 plus 1 is negative 4, so I have a negative on top. Then I have negative 5 plus 4, which is a negative again, and a negative minus negative 3 is another negative. So a negative times a negative is a positive, and a negative times a negative is a positive, and therefore a positive divided by a positive is still a positive. So is this statement true? Are positive numbers greater than or equal to 0? And the answer is yes, they are. So we give ourselves a little happy face. Then let's move on to the next one. So this is the point negative 4 and this is negative 1. So I'm going to pick negative 2 as my test point. So I plug in negative 2 into the factored form. I could plug it back into the original, but I like the factored because it's a little bit quicker. So I have a negative, and a positive, and a negative. And I see that that simplifies to become negative. Are negative numbers greater than or equal to 0? The answer is no. And I keep working through this, going back and forth using test points. So I notice that 0 is available here because this is at 2 and this is at negative 1. So I'm going to use 0 anytime I have an opportunity to use 0. So I have negative, positive, all over positive, negative. This simplifies to become positive. And again, go back through. Negative times positive is negative. Positive times negative is negative. Negative divided by negative is positive. And so therefore, once again, we get a little happy face because that is a true statement and therefore part of our solution. The next spacing here, if we remember, this was a value of 2 and this was a value of 3. Okay, I'm just going to go and put my numbers on the number line here so I make sure that I keep things nice and straight. So if you remember, this was a negative 4. This next term was a negative 1. Then we had a 2, and then we had a 3. So I'm going to go back and pick a number between 2 and 3, which is, let's use 2.5, and then use that as our test point. So plugging in 2.5, I have a positive, then I have a positive, then I have a positive, then I have a negative. That simplifies to be a negative. Are negative numbers greater than or equal to 0? They are not. So that doesn't get a nice little happy face. And the last part of this is looking at a number bigger than 3. Let's use 4. And so I have a positive, a positive, a positive, a positive, and that clearly is a true statement. So if we add little smiley faces to the area that is part of our solution, we can now state the final solution. And here's what it looks like. So from negative infinity to the asymptote, remember this was a vertical asymptote, so it's not going to actually get there, so we use round brackets. And then once we get to minus 1, this is where we have to pay attention. Because the inequality was greater than or equal to, it actually can touch the x-intercept. So between negative 1 and 2, we are going to have square brackets because both of those are x-intercepts, and the equation was greater than or equal to. And then finally, we have an asymptote at 3 all the way to positive infinity. And there is our solution.